Log on, tune in, find out. Another good idea from Cambridge.
Announce the talk of Professor Heinz Langer from Vienna University of Technology. And Heinz is a very classical person, probably the most classical in the both conferences here. And he will speak about Sturm-Liouville operators with singularities and indefinite human products. Unfortunately, last year already gone.
Okay. So thank you very much for nice words, and I'd like to thank the Newton Institute and in particular Malcolm Brown for the invitation. What I'm going to speak about is Sturm-Liouville operators, Sturm-Liouville equations, say L y minus lambda y. We can have a weight here, say Rf. L is Sturm-Liouville operator, and if we are have a regular problem on a bounded interval and with summable coefficients, then our aim is always to associate a self-adjoint operator with this problem, with the operator L. If the interval is bounded and we have boundary conditions, this is easy, this is very classical. If the interval, I should have said if the interval has two regular endpoints. If the interval has one singular and one regular endpoint, this was studied by Hermann Weyl, and it turned out that at the singular endpoint there is a possibility either you have to impose a boundary condition or there no boundary condition is needed. And by in the same way you can also treat the situation where you have two singular endpoints. But what I am dealing with today is the case where the singularity is in the interior of the interval. So the simplest example perhaps one can think of is this equation or this operator in the first line, second derivative and the potential minus 1 over x. We are on an interval which contains 0. So classical or very classical theory doesn't work because here we have a known summable coefficient. We will not bother about the regular endpoints, so I always suppose these boundary conditions 0, that the values should be 0. The first, in fact, paper which I will mention for this example is a paper by a physicist, and he did the following. In order to make the potential regular, he replaced 1 over x by 1 over x minus epsilon and let the epsilon tend to 0. This way we lose self-adjointness or symmetry because the potential is no longer real, but it is the potential is summable. And what he did or what he showed is if we do this and let then epsilon tend to 0, the resolvents of these equations or of these operators converge, and in the limit we obtain a maximal dissipative operator, can be associated with this differential equation, which for the moment I denote by t minus it. Of course, if we know a little bit about Weyl's theory or symmetric operators, then one would do the following. We have here the interval minus 1, 1. So here's our singularity at 0. We can, of course, do the following. We consider this interval and this interval. On these intervals, we have just one singular endpoint. And then we try to stick these somehow together. And so the operators defined on this interval I will denote by S minus. The operator on this interval I will denote by S plus, and then we can take the... Sorry?
We start with C0 infinity. I mean 0 near 0. To define minimal operators, we assume that the function is 0 near 0, right?
Yeah. Okay. So we get an operator, we get a symmetric operator here and a symmetric operator here. It will have a defect, and then the orthogonal sum has defect index 2, 2, and the first to consider these situation where Everett, Ganson, and Settle, they imposed a condition at 0, namely that the functions in the domain should vanish here. And then it turns out that these two operators are self-adjoint, and one consider the orthogonal sum, which is a self-adjoint operator, which we'll denote for a moment by T infinity. Then there was a Ganson coming into this story, and he considered this -1/x as a Cauchy principal value and could also associate an operator with it, which was also later done by Atkinson, Everett, and Settle. About 10, or a bit more than 10 years ago, with Dijksma and Bodenstorfer, we looked at this orthogonal sum as minus and as plus and tried to describe all self-adjoint extensions. And just to formulate part of the result, we consider operators which on the whole interval, such that the functions in the domain are continuous at 0. One can also drop this. And then one finds the most general self-adjoint extension one can associate with this orthogonal sum is given by this interface condition at 0. The limit of the difference of the derivatives should exist and is equal to a real multiple.
So in the case IP gamma is 0, gamma is 0 corresponds to?
Yeah, this gives the gamma, and then these operators which I had with the gamma, they correspond to these operators before. This was what Boyd and Ganson, this is this minus IPT infinity, this corresponds to this gamma. And the T gamma is self-adjoint if and only if gamma is real or infinity. Otherwise one gets maximal dissipative extension. So let's look at a slightly more difficult example. We take a potential Q0 over x squared. Then it's well known if Q0 is less than 3 over 4, then it is limit circle from both sides. So we get an operator with as minus with the fact, as plus with the fact, and we can in some sense stick them together in a similar way as we did in the first example. So this is an example which is, so to say, can consider to be easy. If Q0 is larger than or equal to 3, 4, then 0 is limit point from both sides. This means that this is a self-adjoint operator and this is a self-adjoint operator. And we can take simply the orthogonal sum and we have a self-adjoint operator associated with this problem. And one might ask, what is left here to do? But there were some people, the first was apparently Berezin from physics. They came up that the operator they really wanted to associate with it is not this orthogonal sum. There must be some more complicated operator behind. And that's what I'm going to speak about. And this was taken up by Berezin, then in a certain abstract way by Chondin, Van Dijn, Tip, Dijksma, Corazov, Lugo, Albeverio, I could have mentioned.
I think there was a paper by Berezin about
Yeah. And what they do, they make some construction, some abstract construction, such that they, with the operator up there for Q0, larger or equal to 3 over 4, can associate an operator which is self-adjoint, but not in this simple L2 space, but in a larger space which has the disadvantage that it is no longer a Hilbert space, but it has an indefinite inner product. So, and that's what I'm going to talk about. In some sense, I will try to give an approach to this result, to this self-adjoint operator in this indefinite inner product space, which is somehow more elementary than the constructions by Schrödinger and so on. Probably they are equivalent, but this is. So to start with, forget what I've said so far. We do something else. We consider positive definite functions. This is probably a notion which is known from probability theory as characteristic functions. A continuous function is positive definite if it is defined on some, I always draw intervals here, on some symmetric interval. And it has the property that this kernel, which is here on the first exposed line, this kernel is positive definite. This means that the matrix, all the matrices which we can form with Ti and Tj from this interval are non-negative, or that all these quadratic forms are non-negative. We call or we denote the set of these positive definite functions on minus 2a by p index a, or p0 index a. And the best known case is, of course, if 0 is infinity, a positive definite function on the real axis is the characteristic function of a measure, roughly speaking, or you could say probability measure if we normalize it to 1 at 0. So this is Bochner's theorem. This case goes both ways. So with such a function, there is associated a bounded, non-decreasing function on R, or a measure on R, I will also call sigma a measure. And there is a result by Krein, which is in fact the basis of his considering inverse spectral problems. Krein considered such a positive definite function on an interval minus 2a to a and asked, can we continue it, extend it to the whole real axis as a positive definite function? This is similar to a moment problem if you are given a finite number of moments to determine the measure. Of course, yeah, this almost can be unique, yeah. This is similar to this. You see, in some sense, from Bochner's theorem, the values of f on t are a kind of trigonometric moment of this measure. So Krein's reasoning has many analogies in the moment problem. So Krein's result is that this extension problem from minus 2a to the real axis, 2a to a to the real axis, for a given positive definite function, either we have a unique extension or we have infinitely many extensions. And these infinitely many extensions can be described by a formula. We take again these transforms of the extension, and then we get a fractional linear expression. Here appears a parameter, and this is t, this capital T. So t corresponds to the f, the given t corresponds to the f tilde, and t runs through the set to get all extensions through the set of all never-linear functions. Never-linear functions are those analytic functions which map the upper half plane holomorphically into the upper half plane plus real constants. So also formulas, description formulas of this type are well known from moment problems. Okay? So this is a result from Krein. It goes back to the early 40s. And Krein then 10 years later used this method to solve an inverse spectral problem. Let me try. I will not be too detailed with assumptions, but I will just try to explain the main ideas. The problem is, the inverse problem is, given a known decreasing function on R, to find the Sturm-Liouville operator or a canonical system, which is slightly more general, which has this sigma as its spectral function. I will not go into definition what this is. We do not really need this here. So, but just to mention it, you take Fourier transformation, and then with in the L2 sigma, you get Parseval's identity through the Fourier transformation. So, let me sketch this Krein's method to solve this spectral problem. Given a sigma, he wants to construct a canonical system which has this sigma as its spectral function. What does he do? First, with the sigma, he associates the corresponding positive definite function. Next step, this positive definite function he restricts to a finite interval, -2a to a. Then we are in the situation which I spoke about a moment ago. This Fa can have a unique continuation as a positive definite function, or it can have infinitely many continuations. Let's assume it has infinitely many continuations. If this is not the case, one can achieve this by changing the sigma or the f a little bit. So, but this is detail I won't. And then he does the following. He asks for all the positive definite extensions of this positive definite function. As we know, or as I told you, they can be described by such a formula. Earlier we had this for a, now I put the a equal to x, and this is, so to say, an arbitrary positive definite extension of this function f with an x, and the description is here again fractional linear transformation through parameters, all Nevan-Linder functions. So, and now comes the interesting thing. Now he considers this matrix function as a function of x. And then it turns out, with respect to x, it satisfies a canonical differential equation on 0, infinity. So the canonical differential equation here is in the standard way. This is a 2x2 Hamiltonian, real. That's it, and locally summable on 0, infinity. And then there comes something up like trace normed or things like that. And it turns out that the given function sigma is the spectral function of this canonical system. And now in a nice situation, one can transform the canonical system into Sturm-Liouville equation and things like this. So this is roughly the main idea behind Krein's method solving inverse spectral problems. Of course, there are, this is a very rough sketch only because in general these sigmas are not bounded, and then this doesn't make sense, so one has to replace this by a more general kernel. But these are details which are not so important to us at the moment. What I will do is the following. I will have a look at this procedure from a certain, well, just from a very far away point. So given a sigma, with a sigma we associate a Hilbert space. In a Hilbert space L2 sigma, we always have the operator of multiplication by lambda. Second object which interfered was a continuous positive definite function. And with such a continuous positive definite function, one can always also associate a Hilbert space. As follows: take this kernel and form this integral. Because of the positive definiteness, this is a non-negative inner product. If we use nice functions phi and psi, for instance, once or twice differentiable or only continuous. So this set, if we take factor and complete it, we get a Hilbert space which is associated with this positive definite function f. And in this Hilbert space there is a generic operator, and this is the operator of differentiation. And it is easy to see that in this inner product, if we insert some condition at the endpoints, for instance, that all our functions phi and psi are 0 there, this operator is symmetric in this inner product and generates a symmetric operator in this Hilbert space. And this symmetric operator is self-adjoint, for instance, if we are on the whole axis. And this means, in fact, that this, since the sigma is, I suppose now the sigma is the function in the representation of the f, this means we have, for this operator of multiplication by lambda, we have another representation in another space, but these operators are unitarily equivalent. So from a spectral theoretic point of view, they are the same. And now we have our third object. This is the canonical system. We assume we can, all these additional conditions which I didn't speak about are satisfied. We find such an H, we find such a canonical system. Then with H, also a Hilbert space is associated. This time these are two vector functions because H is non-negative. Maybe I didn't mention this. H is non-negative in 2 by 2 matrix function.
Will it be trace normed?
Sorry?
Trace normed.
Trace normed means that the H is a function of x, so the trace of H of x is always 1.
You can always remove.
You can always, yeah, by introducing a proper variable. This brings the thing, in fact, always to the interval 0, infinity.
I see.
So if there's nothing, then H is continued somehow. Then it becomes unique more or less if you impose such a condition. And in this Hilbert space, we have the operator which is given by the canonical system. The canonical system was G dx, and the H was on the right-hand side. If such a weight is on the right-hand side in an equation, you bring the weight into the equation and take 1 over R to the L. So if one has an equation here, one considers the space L2 with weight R, yeah, and then one considers in this the operator 1 over R times L. This is the same here with the H. This is why the H inverse here appears. This corresponds to this R inverse. So, and being a spectral function for the sigma means that this operator and this operator are also equivalent. So all these three operators are unitarily equivalent. The canonical system, the positive definite function, and L2 sigma, okay, these all equivalent images, or how do you say, of the same operator. So I will give an example for this in a moment, but first a slight generalization. so far this kernel was positive definite. One can also suppose that it is not positive definite, but has a finite number of negative squares, which means that for all these quadratic forms which we have associated with this kernel, each of these forms has at most one negative square. Or if we form these eigenvalues f of ti minus tj, eigenvalues of these matrices f of ti minus tj, all these matrices have at most one negative eigenvalue. Yeah? This class of functions was also introduced by Krein, and for this class of function, essentially the same theorem holds as for positive definite functions. One can ask for extensions. Of course, this number of negative squares cannot decrease if we make the function larger, because we get more matrices. And it's possible that it increases.
So it can increase.
It can increase, yeah.
But
yeah.
quite nice, right?
It can increase.
Yeah.
Yeah. So I will give an example in a moment. Just keep in mind that the same formula holds also if this f is has one negative square on the interval. So now let's come to an example. This is from a paper with Matthias, Zoltan Shashwari. We consider a very simple function, this one. On this interval, this function as it is here, on an interval smaller than with 2, it is positive definite. This follows, for instance, from a theorem of Poya. It says that any function which is convex and tends to infinity if t goes to tends to 0 if t goes to infinity is positive definite. And of course, you can this here in infinitely many ways continue to a function which is convex and goes here to 0, continuous. So in this case, we are sure we have infinitely many positive definite extensions, which can be described by this Krein's formula. So we can go a little further. We can go to 1. This is still a positive definite function, which still follows from the theorem of Poya. We can make it a little bit larger, and one can show that this is still positive definite and still has infinitely many positive definite extensions to the real axis, which can somehow be described. And we go further. We go to 2, and then it turns out that this function has exactly one positive definite extension. And this one positive extension is the periodic extension. That another extension like this, which is natural one can to consider, is not positive definite, follows immediately from the fact that for a positive definite function, any value is in modulus less than or equal to the value at 0. This follows from the integral representation. If you just estimate this e I lambda t under the integral by 1, you find this inequality. So this cannot be positive definite, but one can show that the corresponding kernel f of t minus s has exactly one negative square. And it remains in this class, we get one negative square, how large we choose, always one negative square. Okay, so now what we did is we looked for a description of all these extensions. This is a concrete example, so we can really calculate the extensions. And this we did, and we found the matrix function which gives this description, and this is this matrix function here, which works for all A different from 1. A different from 1 was an exceptional case. Yeah, there we had one positive definite extension, of course infinitely many extensions with a negative square, but we forget this point for the moment. But if we are larger than A, then this is a fine matrix. It will give a description according to this formula, then of all functions which have one negative, or for which the kernel has one negative square. If A is smaller than 1, they are positive definite, and then so. Now what we did before, instead of a fixed A, we consider this as a variable. So we have this function of x. And this should satisfy, according to this general result which I mentioned, should satisfy a canonical differential equation. And this canonical differential equation is surprisingly easy. It's not trace normed, unfortunately, but it's date normed. But this is just a transformation. Here the determinant is always 1. This is the other way to normalize, or a useful way to normalize a function. But you see, this is not within the classical theory of canonical systems, because this has a singularity at 1. And a singularity at 1 where the A which is not summable. So the fact that the number of, if A goes through, or x goes through 1, a negative square appears, means that here appears a singularity. And here is this matrix function again. Actually, this was all already on the screen. So we are led to consider, so far the W was the matrixant of the equation. Yeah, if we go to the equation, we go to a vector function. This is the canonical system. This is now a 2-vector function with this Hamiltonian, but it has a singularity which is not summable at 1. So this is the situation where x is somewhere between 0 and so this time at 1 we have a singularity. This is of course I write the third situation. So we are here. Now we have a singularity at 1, and our right endpoint is always here. So the singularity from 0 is shifted, but I hope this is not so. For this example, it's natural to have this singularity at 1. So let's just write the corresponding second order differential equations. If we transform the first order system of second order equation, for the second component, we get this equation. They are both now in this impedance form. For the first component, we get this equation. We will mainly be interested in the second component here, in this equation. And if one makes this substitution, for u, we get the Bessel equation. But with a singularity at 1, in usual Bessel it's at 0. But this doesn't really matter. Well, we are now on an interval, 0, A, or A is equal to infinity, and the singularity is here. The singularity is here in the interior of the interval. So we want to associate with this problem on this interval, say, with this differential equation, an operator. You see, at the beginning I sketched this correspondence between, so to say, positive definite functions and Hilbert spaces. Now the corresponding function f for this interval, this had one negative square on this larger interval. So what is to be expected, that also in this representation by a differential operator, this operator will act in a space with one negative square, and this means in a space with an indefinite inner product. So this is now our aim, to study this equation, or actually we start first more from this equation. And I must just have a look. So what shall we do? You see here we have a Sturm-Liouville equation. This is actually the situation where we have a weight on the right-hand side. Actually, this was wrong. The weight should, of course, be also here in front of the lambda, and here we can forget it. Sorry. This is just the right-hand side. And if we study such equation, I mentioned this already, one introduces the operator L2R, and with the weight R. And 1 over R goes in front of R. So what is our weight R? Our weight R is this factor on the right-hand side. Lambda is equal to z squared. And this equation is, of course, the homogeneous equation to this. So this corresponds to here 0. Okay? So if we look at the classical theory, we would introduce the space L2, and now the weight is 1 over x minus 1 squared. But this is, of course, a weight with a singularity. And the L2 space with respect to this weight is nothing else than the L2 space here plus L2 space here. So this doesn't give anything. So we must look for something we can replace this space with. And this something is one of the very first examples, for instance, in the book of Gelfand and Shilov on generalized functions. This is a way to associate with such a singular function a distribution. And the distribution is defined as follows. You see, the point is that this is not a finite measure. But in order to define an integral with respect to this singular measure, one can do the following. Here we have a singularity at 1. So we make the function we want to integrate, we want to find the distribution at, we choose it smooth, and take off here so many terms that the singularity will be killed. This is the usual way to associate a distribution with such a singular measure. And since we deal here with f0, one can also add some, the value of f at 1 with some coefficient. So this is, so to say, the point in the approach which will I sketch now to these problems, that we use this distributional interpretation of the generalized function. And with this interpretation, we can define an inner product just by applying the distribution mu to this product fg bar. Take, for instance, twice continuously differentiable function. And then it's easy to see if you replace here f by fg bar, everywhere that this can be written in a different way. This is an identity. One always should, of course, keep in mind that all the integrals exist. But they do. We have supposed that the singularity is here is not too big. It's only 3, so this is only 3/2. And if f has a derivative, this is finite, and also these integrals exist.
It's less than 3/2.
So?
It should be strictly less than 3/2, right?
Yeah.
Strictly less than 3/2.
Yeah. So, and here appear these mixed terms, f, g bar, and here we have the integral. And this we can write slightly differently. We can introduce a mapping this was the term under the integral. This one, perhaps I should show this. This one were the important ingredients. This here is, so to say, more or less an L2 space, two L2 functions. Here we have a constant which depends only on f. Here we have a constant which depends only on g. Yeah? And here we have the corresponding symmetric things. So we can write this sum in the following way. We introduce this function in L2 and these two constants, write these as a vector, and then the inner product, which was on the last slide, is just jf, jg with this matrix as Gram matrix. And this Gram matrix has always one negative eigenvalue, yeah? Because here is this 2 by 2 scalar matrix, and this has one negative eigenvalue. Everything is positive. So, and this means, in other words, this inner product has one negative square, and such spaces with inner product with a finite number of negative squares, they can be completed as Hilbert spaces. They are usually called Pontryagin spaces because any finite number could be any finite number. You can split off a one-dimensional space and consider the orthogonal complement in this indefinite sense, and then on the orthogonal complement, this is a pre-Hilbert space or so. The inner product is non-negative definite. This is, roughly speaking, the proof. So this is not very much. So we end up with the completion is a space. This is L2 from this first component. Completion then becomes all L2, and then here we get both twice the whole complex plane Z. So roughly speaking, the point is that here this and this are not continuously dependent on this term. So this is why this completion gives this space. So this is a simple exercise, so to say, in function analysis. And we can, of course, consider the inverse mapping. If you look at the first component, if we put this equal to u and solve this equation for f, then we get what is written here. So?
Z2 is not involved.
No, this does not enter the first component.
That's true, yes.
This doesn't enter the first component.
So it's not true, is it true it was from both sides? I mean, it is both left and right inverse?
Yeah. No. This is
only one side.
Yeah.
One side, yes.
Yeah. So, and what we now do is, and this is actually the what I want to speak about. We consider this operator with a slightly more general exponent here. It was 2 in the example. we make it slightly more general, and we want to associate an operator in a space with an indefinite inner product, even in the, just in this Pontryagin space, which I explained a moment ago. This is the corresponding eigenvalue equation. Here I wrote, this is the weight is 1 over, so 1 over the weight what I have here is this factor. And the relation with the Bessel equation is that by this substitution it becomes a general Bessel equation. We have the singularity at x equal 1. Alpha is restricted always between 1 and 3. If alpha becomes larger, the number of negative squares will increase. So this...
you need to subtract more.
Yeah, one needs more components as the singularity increases. So what we do is the following. We transform this equation into an equation for u under this mapping, I hope. Yeah, here it's written. U was the first component of gy. If y satisfies the equation which was here a moment ago, we look for the equation which is satisfied by u. And this is an more or less straightforward calculation. Here we have the y still in the equation. Of course, this we do not want. For the example, alpha is equal to 2. Everything becomes explicit. In the general case where alpha is, we can also write down these formulas, but Bessel functions are involved. I won't go into details, but these functions are nice. Even these singularities here, they cancel. And this term can, for alpha equal 2, become simple. It's just the derivative at 1. So the equation we get is this differential equation. So what we have, what is the unusual thing? The unusual thing, this is a potential which is of delta type or delta prime type. In any case, a singular potential which is concentrated at 1. So with this respect, it's not a classical equation. Now this was, the u was the first component in the vector y. This satisfied one of the equations. U was the first component. The first component satisfies this inequality, and one can calculate the other components. For simplicity, this is here for alpha equal 2. The last component was such an integral at the beginning from the formula, but this can be calculated. It becomes rather easy. The value which appears is this u prime at 1. It appears also in the other components. And this is now the operator which is associated with the differential equation. So the space has been blown up. And so to say this, and this are added. Originally, we started with the singular equation here, but we were aware that we should give an interpretation to the singularity. And this is just one way to do this. Now one can look for symmetry conditions. Now we are in this Pontryagin space inner product. And this is just inserted what A is. So one can get this expression. Symmetry condition will, of course, mean that this should be real. So we should conditions that this is a real expressions for all elements in the domain. I did not specify the domain, but this was done. And just from here we go. Just rewrite the last formula. Now what is on the first line is real.
So this AAUU, right? Well, A division 3 radical U is quadratic form. It's quadratic form for this A, right?
Sorry?
This is quadratic form for this A.
This is quadratic form for the A. Yeah, for the big operator. For the big operator, yeah. And now one should impose self-adjoint boundary conditions at 0 and A at the endpoints. We are not so much interested in, so then these terms will also be real. And then we have to care for these two terms, and this is what I said. We fix the boundary conditions at 0 and A, and then one can this A0, this was a certain freedom. This came from the inner product. This was a certain freedom we have in determining the inner product. So if we choose this very particular, then the form becomes like this. And then we have just to make sure that this is a real expression and this is a real expression for all vectors which contain u, xi1 and xi2 of the domain. So, and this is means just that this is proportional to this, and this is proportional to the expression which was as a factor there. So we get boundary or interface conditions, perhaps I should say, corresponding to this, to the singularity 1. And as you see, there is quite a great variety of possibilities to choose. We can choose S and T, any real numbers or infinity, and we can also choose this A0. So this is a rather vast set of, in the above example from where the operator is more or less determined by the fact that it corresponds to this extension problem for this particular function. The self-adjoint operator, according to the scheme I had at one place, is fixed. And then the unitarily equivalent operator is given by these boundary conditions at 0 and A, and these two conditions at 0. So the second component is determined, xi1 is arbitrary. That means the corresponding operator has the eigenvalue 0, and u at 1 is also 0. These calculations describing all the possible conditions at 1, they can be made a bit more compact by using these boundary functionals, but my point here was not to describe all the whole variety of this. I just wanted to show these ideas. So one ends up with, here's the operator again with these simplifications when these terms go. This was the original operator with singularity, and the interpretation, of course, there's always a certain arbitrariness. The interpretation here is this operator with 3 components and this additional term in the differential equation. So this is all I wanted to speak about. Thank you very much for your attention.
Question, comments?
sometimes with these problems where you're looking at a singular problem, a natural thing would be to get rid of the singularity by making a transformation of the independent variable, as I say, 1 over x to z or something like that, and then you end up with again with a problem which in fact now I guess you have a weight function which is not singular but in fact is indefinite.
Yeah, okay, but I don't think that the singularity can be get rid of by any transformation.
No, but I was just thinking in
You put it into
way,
the weight function, yeah.
Yeah, and then sometimes then you can think about, instead of looking at a Hilbert space with an indefinite weight, you can then associate a Dirichlet form with the left-hand side of the operator.
Yeah. But in the singular case, I don't know if this has been done in case of such singularities. I'm not sure. Of course, if the singularity is at the boundary point, then one can consider these left definite problems, and can also consider problems which are not left definite, but the left form has a finite number of negative squares.
Yes.
But I don't know if this is yes. What was studied, and these papers which I quoted by Shondin, Albeverio, and Korazov, they are, they consider the Bessel operator, so, and then the singularity is here. And they introduce indefinite inner products also for the case that the singularity is at an endpoint. And this is motivated somehow by the fact that the spectral function which appears for such a problem, if one chooses a suitable Fourier transformation, is rather singular. It is more singular. Usually the spectral function grows such that 1 over 1 plus lambda is integrable with respect to sigma. And but in this situation, the spectral function can grow much faster. The spectral function for a particular Fourier transformation. And they come to constructions which are very similar to these constructions, in this case of a singular endpoint. But this, I think, one can overcome by different methods, whereas with the singularities in the inside apparently does. At least I don't know.
I have the following question for mine. You know, these sort of singularities in relative equation, as Brian knows also, is somehow what goes on in indivisibility.
Yes.
So, did you look at, it's probably some particular case of this correlation between left and right hand that gives right to indivisibility. Did you look at that?
No.
I mean, there's basically indivisibility when these two parts splits apart, right?
Yeah.
So, and in some
So
conditions...
it's sort of blowing up the singularity somehow.
Yes, right.
Yeah.
So, and exactly when there appears singularity in the coefficients of relative equation, when there appears. So that's probably maybe something to look at because yes, so.
What is also left open is to compare this construction with the abstract constructions which are mentioned by Shondin.
So what, I mean, I don't know, what happens to the sort of deficiency index problems when you're working in Pontryagin spaces? And do you have an analogue of the via limit point, limit circle? I mean, what sort of structures do they have in this setting?
Yeah, we have no limit point, limit circle. This is always one situation. We have always limit circle in some sense. We can impose many boundary conditions. You see, at the end. So, but the description of all the self-adjoint extensions is not as easy, apparently, as it is in the case of a Hilbert space, where you get the parameter set is rather well determined. Here, the parameter set seems to be more complicated. In particular, because of this choice of A0, that we can choose the inner product. These are all data which are not in the original equation.
And this A that you have here at the end, it has a non-real eigenvalue, or?
Yeah, this is always in the pi1 space, and the case of the example here, this has so it has one eigenvalue with a non-positive eigenvector, roughly speaking. In this case, it's at 0. Often it appears at infinity, but we are quite sure that with certain boundary conditions we can put this eigenvalue anywhere in the complex plane.
And is there an interpretation for this particular eigenvalue? Or can one compare it with the orthogonal sum of the two separate operators in the Hilbert space situation?
This orthogonal sum is somehow it plays some role at some place. And in the abstract theory, this is the starting point, you see? But in the abstract theory, which I did not speak about here, there also appear many parameters, and it's also then you have conditions on the parameter matrices. So the point here was actually to introduce this distributional weight and as a starting point, and to get, so to say, this blowing up in a natural, for me, natural way, put it this way.
Thank you very much.
Okay, thank you.